Hello. Today we're going to go over the two variable Taylor series derivation, a very intuitive derivation that will not talk about the remainder. And then we will also use the two variable Taylor series test to explain how the second derivative test works for a function of two variables. Now, this will be very intuitive. If you're taking a course in real analysis or advanced calculus that demands rigorous proofs, this video will be a little bit too elementary and not rigorous enough for you. But it should at least give a little bit of an idea of what's going on. So let's get started. All right. Get rid of this, and there we go. So that's what it is. Two variables and second derivative tests. So the first thing we're going to do is we're going to talk about the Taylor series for two variables. And we will assume that all partial derivatives are continuous near some point x naught, y naught. And the points x, y will be within this region. Let's call it some open region here. And any point that of interest, the all the partial derivatives will be continuous in this general direction. Now, what we're going to do is, first of all, I want to remind you of the Taylor series for one variable. And this is sort of one variable. And what happens here, and I'm going to assume it's expanded about x equals 0. And we know that g of x will be g of 0 plus g prime of 0 times x plus g double prime of 0 x squared over 2 factorial, which is just 2. And what I'm going to do is I'm going to focus on these terms right here. And I'm going to also assume that these remaining terms we'll label that to be the remainder after 2, and we'll assume that the remainder goes to 0 as you get closer and closer to the initial point, and or if you go out far enough, that's what I should say. If the values of x get high enough that this, oh, how can I say it? Yeah, that this remainder term goes to 0. Now, okay, now let's get on with the two variable case. And the two variable case, what I'm going to assume is I'm going to assume that you have a function, f of x, y, and an initial value of x naught, y naught, of x naught, y naught being put into this function. And so I'll just go ahead and do this. And here's the value of interest, x, y. And what I'm going to do is I'm going to make a little line segment going from here, this point to this point. And here's how I'm going to parameterize my line segment. I want to parameterize it using a curve R of t, where the x value will be xt plus 1 minus t times x naught, and then yt plus 1 minus t y naught. So that is the line segment that for t equals 0, we're here, and for t equals 1, we're here. And we're always along this line segment. Now, the value of doing that is that you've learned how to compose functions, and so you can now talk about a function, g of t, being what you get when you compose f with this r. So that's going to be f of xt plus 1 minus t, x naught, yt plus 1 minus t, y naught. Okay? And notice that g of 1, if you plug in the 1 here, you basically get f of xy, and that g of 0, that's a 0, that's a 0, that's a 0, that's a 0, that's going to be f of x naught, y naught. Okay? So we have that, and we're evaluating a function along this line. Okay? Now you've probably learned the chain rule. Since this is a function only of t, it makes sense to talk about its derivative. And we're going to need the derivative because we're going to be using the one variable chain rule. And you probably learn from the chain rule that that's going to be the gradient of f dotted with r prime of t. Now let's look at what r prime of t is. Well, the derivative with respect to t is x. The derivative of this with respect to t is minus 1. And the same thing on the y direction. The derivative with respect to t is y minus y naught. Okay? That's what that derivative is. This part here, you know, is a gradient. So this is going to equal the partial of f with respect to x, and the partial of f with respect to y, dotted with so g prime of t will be the first partial of f with respect to x, and we have to, okay, evaluate it at a point times x minus x naught plus a partial of f with respect to y times y minus y naught. But remember, when we go to plug into the Taylor series of one variable, we got to plug in the 0 here. And remember, our g of 0 is going to give us the inputs of x naught, y naught. The same thing applies here. So g prime of 0 is going to be the partial of f with respect to x, evaluated at x naught, y naught, x minus x naught, plus the partial of f with respect to y, evaluated at x naught, y naught, times y minus y naught. So this entire thing here, that is going to give us the first term in the Taylor series. I mean, besides the constant term. So we now have for our Taylor series, we've now got the first part, the Taylor series, and that's going to be g of 1 is going to be g naught plus this thing here. So we've got this term, and remember this term here is this. So we got our first first term right here. Okay, so now we want to work on the second term. In order to take the second derivative and then plug in 0, we need to go ahead and work on this. So what is the second derivative? We need to calculate that. Well, the second derivative is going to be the derivative of the derivative, which is a first derivative of what we have here. So what we're going to cut and paste, we're going to take this thing here. Like so. And as you know, the derivative of the sum is the sum of the derivatives. And keep in mind, with respect to t, this is a constant. And we got to take this derivative here as well. And this is a constant with respect to t, right? So now we have to use the chain rule again. But we're using the chain rule in this case with the first partial. And what happens there, that's going to be the partial of x of this times the derivative, in this case, since it's of t, times this part right here, because remember, this part here is x prime. Plus the partial with respect to y of the partial with respect to x, right? Y minus y naught. And all of this gets multiplied by x minus x naught. And then we have to do the same thing here. So following the pattern, we have the partial of x of the partial of y plus the partial with respect to y of the partial with respect to y, all times this constant right here. So the second term of the Taylor series, and we're going to do a little multiplication, but this is going to be the second partial of f with respect to x twice. X minus x naught, this times this squared. Now I'm going to go ahead and write it this way. Y minus y naught, x minus x naught, plus, now we're going in the other order. So let me fix this up a little bit. So this is an f here. Okay, x minus x naught, y minus y naught, plus the second partial of f with respect to y twice. Now, you learned earlier that if all the partials are continuous, and I guess we need the second partial continuous here, then by Clairaut's theorem, you can take the partial derivative in any order, and you can multiply in any order. So the second term is typically written this way. And there's two of these. Well, this isn't quite the second term yet. Plus Okay, now keep in mind that all of this is G prime, double prime of T. So when we now go to plug this in to this formula here, we have to use a 0 and we have to divide by 2. So the second term at T equals 0 will be 1/2 second partial f second. Oh, there's a square here. And we're just writing this down. And there's a 2 because there's 2 of them. And then there's a single one here. Okay, so there is your second term for your two variable Taylor polynomial. Now, let's see what happens. And again, plus a remain, and then there'll be a remainder term as you keep going. So now, if we are at a critical point for f, this means that the first partial is 0 with respect to x and respect to y. That's what it means to be at a critical point. So it basically means the first, you have your constant term, and then you have your degree 1 term. Is what corresponds, that's what this is. And that's what corresponds to this. So now what I'm going to do for ease, well, I guess I don't have to do this for ease. So at a critical point, we get that f of xy will be f of x naught, some constant, plus this stuff here. And I'll just go ahead and use this notation here just because it doesn't take as long. And I'm understanding that you're plugging in x naught, y naught here. Plus this other thing here. Better scroll down. Plus your remainder here. So it's going to look like that. All right. And I'm going to kind of not pay too much attention to this constant because you can always just subtract a constant and just get the variable part of the function here. But at a critical point, this is your first non-constant term, and that's going to determine how your function behaves. And now we're going to move and work toward getting the second derivative test. And so what I'm going to do for ease of computation, I'm going to let A equals f sub xx of x naught, y naught. I'm going to let B equal f of xy with x naught, y naught in, and C equal f sub yy. Okay. And I'm going to look, I'm going to kind of ignore this here because I can always be subtracted off and all that. And what I'm also going to do for ease is that, and just for the sake of argument, I'm going to go ahead and let x naught equal 0 and y naught equal 0. That's easy to obtain by a very easy change of variable. You just take your x naught, y naught, and subtract that off to turn it into a 0. So, so what I'm going to actually look at is I'm going to look at the function, uh, and I'm ignoring this half for right now, but I'm going to look at a x squared plus 2b xy plus c times y squared. So I'm going to let y minus y naught is y, x minus x naught is x, setting these equal to 0 just to keep them out of the way. And so I'm going to look at this right here. Now, the very first thing I'm going to do is I'm going to notice is that f of xy is approximately f of x naught, y naught, the constant, plus 1/2 times all this stuff here. And let's just make this 0 and 0 here. Near 0, 0. So this is what's going to determine what kind of critical point you have. It's going to be strictly this, and plus a remainder term, which I'm going to ignore. So let's take a look at this. Now this polynomial function, I'm going to divide out by an a, assuming that's not 0. And I'm going to have an x squared plus 2b over a xy plus c over a y squared. Now, here's what I'm going to do. I'm going to take these two terms right here, and I'm going to complete the square. And when you complete the square, this is what happens. This is a, we have this outside, x squared plus 2b over a xy. Then what I'm going to do is I'm going to divide by 2 and square it. So plus divided by 2, squaring. Now I'm doing this coefficient here. So divide by 2 and square. And then I have a y squared. But because I added that, I better subtract that. Like so. So I didn't change anything because I added and subtracted exactly the same thing. This now becomes a, this is now x plus b over a y squared. Okay, that's exactly that. That's why we completed the square. Plus a times all this. Y squared. Now we're almost ready to do this. What I'm going to do now is I'm going to write it like this. And I'm going to multiply this through by a, and I get c minus b squared over a y squared. And then I'm going to do one more thing. I want to get a common denominator here. So I'm going to do this. So I have a square here. Then I have CA minus B squared all over A Y squared. Finally, we're at somewhere. Now, what's this have to do with max, min, or saddle? Well, keep in mind that this is a square and this is a square. So let's look at the possibilities. Now, suppose, so first case, suppose A is positive and CA minus B squared over A is positive. Then you have the sum of two squares. The sum of two squares, positive sum, to fx naught y naught, the constant term. So that means this part is positive and this part is positive. So if we're adding, when we move away from x naught, y naught, and we're adding something positive, this means that x naught, y naught, whatever that is a local minimum. That's for A positive. But for A positive, but since this is positive, that means CA, the numerator, must be positive as well. Okay, so that's this thing right here. And remember what A was. So that is your classic local minimum. Okay. And remember, this part right here is what we defined in class to be D. So that gives us a first thing right there. If A is positive and CA minus B squared over A is negative, well, that means we can, by letting, oh, I forgot my x squared here, but by letting, let's say, y be 0, we can add when we go in the x is not 0 direction. But if we let x equal 0 and add in the y direction, we're going to get more negative because this coefficient here is negative. So this is a saddle. But let's just take a look here. See if there's any more room. There isn't. So, and we'll just do a new one. But so let's just go ahead and write this. Well, I better put an x squared here too. So let's select this and copy. All right. So what we were doing here is we were doing the case where A is positive, but CA minus B squared over A was negative. But since A is positive and this whole thing is negative, CA minus B squared is negative. Okay? Now we still have a couple more things to check. Now let's check A is negative. Now if A is negative and CA minus B squared over A is negative as well, that means that when we start at f of x naught y naught, and we move in any direction at all, we're subtracting two positive things. Two, because this would be negative and the A would be negative, so we would be going down. This is a max, a local max situation. But if this part right here, if that part is negative, but A is positive, that means the top, the numerator, must be negative. I'm sorry, must be positive. because these have to have different signs, right? For this whole thing to be negative, these two have to have different signs. So if A is positive, if A is negative, the top has to be positive. And once again, this is your D being positive. Okay? And again, this is your f sub x being negative. Sorry, I should have written it that way. Right. Opposite sign. All right. In the last case, if A is negative and the other one is positive, this is a saddle because this means you can go down by going in the x not zero direction and the y equals zero direction. Right. And then you can go up by holding x equal to zero, changing x equal to zero and letting y vary. That's clearly a saddle. But again, CA minus B squared and A have to have the same sign. So CA minus B squared is negative. So that gets us to our second derivative test. Where D is f sub xx, f sub yy minus f sub xy squared. And these are evaluated at x naught, y naught. And if we have D is positive, that's a max min. Where if this here being positive, it's a min. That's a max. And if D is negative, we have a saddle. And if D equals 0, it's inconclusive. So that is a little bit about the second derivative test for two variables. It does use the Taylor polynomial. Again, this has been sketchy and non-rigorous. To be really rigorous, you would have to deal with the remainder term and things like that. But thanks for watching.